And the next question is something like this. From a steady state RC circuit, what does it say? 10 volt and each resistance is 2 ohm. So we got to calculate the potential difference across the capacitor. Okay, finally at steady state the capacitor acts as open circuit. That means, this resistor will be out of the picture when it comes to steady state. Since this is in series with capacitor, so no current goes there. Now, this is 2, 2, that will be 4, okay? And 4 and 2, they are in parallel, so that's 8 by 6 in series with 2. So the total resistance 8 by 6 is 4 by 3 and 2. That will be the value of R net, and R net is going to be 10 by 3. So once you calculate the net resistance across this terminal, how much will be the current? 10 by 3, and that is going to be 3 ampere. That's how it comes. So now we have calculated the current. Now this 3 ampere will get divided. Let's see. The first root will be this one. And remember, this and this, they are in series. Okay? So how much will be the current? 1 ampere will go here, and of course 2 ampere will come here, and then the same 1 ampere will also go there, and here that's going to be 3 ampere. Now we need to calculate the potential difference across capacitor C. So if I call this point by, let's say, D and this point as E, now I can say the potential difference across capacitor is VDE as well, since R5 is completely functionless. Let's see how much is the value. 1 into 2, that's 2 plus 6. This value is going to be 8. And 8 will be the correct answer. Question number 25, the final question for this shift. Let's see. So here is question number 25. It's from geometrical optics. So there is a light ray entering a solid glass sphere. I think we better make a figure, and side by side we can analyze all those things. So here is that glass sphere with the refractive index √3. And it enters at an angle of incidence which is 60 degree. Fine. So let's make the condition here. If the light hits here, okay, let me make the normal as well. So here till the center, that's the normal. And then the question says it's at 60 degree. Further, let's try to trace the ray diagram. Rarer to denser towards the normal. And let me make a normal again here. So starting from this point, this is another normal. And now what it says, the ray is both reflected and refracted at the farther surface. So that happens, partial it's reflected, partial it's refracted. So that's not a problem. So this is the reflected one, and the refracted one is going to go in this way. So I'm ready with the diagram, and we need to calculate the angle between the reflected and the refracted ray. Let me first give the arrow here that will give the direction of the rays. That's great. And this angle is 60 degree. Let me call this by R, the angle of refraction. Let's see. Using Snell's law there, 1 sine 60, that will be √3 by 2, is mu sine R. So that means R will be 30 degree. So here this is 30 degree. And if this is 30, even this angle would also be 30. The isosceles, these are two radii. And finding this would be a straightforward, you can think from reversibility, from air to medium 60 to 30. So from medium to air 30 to 60, that's how it goes. And this, the angle of reflection has to be equals to angle of incidence. So we need to compute the angle between reflected and refracted. So that's 180. So this angle is going to be 90 degree. And that's what our answer is going to be. The angle would be 90 between the final refracted ray and the reflected ray. So with that, we come to the wrap, and this was the solution for the evening shift for the question paper that was placed on 2nd September 2020. In the entire series, we would be solving each and every papers of all the shift. I'll see you there in the next paper. Take care. Bye-bye.